All right, so here is the wrap up for part 4 of the lab, the long, torturous lab that's almost done. All right, part 4 is the EK. All right, so the first thing that we just want to think about in terms of this cart is if I have a cart and it's not moving, okay, and then all of a sudden it is moving, right? Okay, how does that happen? So if I think about it in terms of forces, I say the cart is at rest, okay, and the forces are balanced, right? Because originally when I start off, I only have an FG, cart earth, and an FN, cart track. This is the cart, all right? And it's not moving. How do I get it moving? Well, I have to apply a force to it, right? I have to like put my hand in here, whatever. Oh, I have too many fingers. Okay. All right, and push the cart so that during the push, I still have my FG and my FN, but now I also have an FN pointing this way, cart hand. Okay, and we're gonna assume this is frictionless just to keep it easy. I know, you don't like it. Okay. Now the forces are unbalanced, okay, which causes a change in motion so that now the cart is moving, okay, and then once we get to this stage, if he's just moving and I'm no longer pushing it, I'm back to the same balanced forces, and the cart is just sailing along at a constant velocity. Okay, so that's like the old way that we would describe it, okay? The new way, in terms of energy, it's kind of the same thing. In the first picture, I would say that the cart has no energy. And then by the time I get to the third place, it has kinetic energy. All right, well, how does it get that? It can't just automatically show up. In this phase, I have to do work on it. I have to apply a force through a distance, right? I have to push with this force for some amount of distance that the cart moves, and then I do work on it, which in turn gives it kinetic energy. Okay, so that's the difference in how you're going to explain it. I think that's in somewhere that you need to write. Okay, so the difference between explaining it with forces in motion, which is like the old way, and explaining it in the new way. Okay, we also could have explained it, right? This one has no momentum. I apply an impulse and I get momentum, right? That's another way to explain it. Okay, but right now we're going to focus on the energy way. So it has no energy, I do work on it, and then it gives it energy. Okay, this is the part that we care about. Okay, this is the focus part, is this during, whoa, I can't spell either. This is the during the push part is the part that we care about, because before we don't really care, it's not moving. Afterwards, it's already moving. We care about this change that's happening. Okay, and that's the part that we're going to focus on. So how does that look? Okay, again, we're going to do 3 different things to it. Okay, and remember, this is all during the push. This doesn't match the last 3, okay? This is during the push only. This is just the middle part. And again, we're going to look at the force versus distance. Right? Okay, now, let me see what it said. Try to see what the numbers were. Okay, here, this part. Okay, so 10 and 0.4, 10 and 0.2, 5 and 0.4. Okay, let's see if I can remember that. All right, so the first one we're going to say, let's assume that I push the cart with 10 newtons of force over a distance of 0.4 meters. Okay, so then my energy force distance graph is going to look like this. Okay, the area is still base times height. The base is 0.4 meters, and the height is 10 newtons. Okay, so this is going to give me an area of 4 joules. Again, do you see this is the same thing over and over? I still have joules because this is still a force versus distance graph. I'm doing 4 joules of work to give the car 4 joules of energy. Okay, that means I push 10 newtons for, a pretty long distance, right? I also could push 10 newtons, but maybe I only push it half as far. Okay, so when I calculate this area, I'm only getting 2 joules of work out of it. He's only getting 2 joules of kinetic energy, which means he's going to be going slower. right? Which makes sense. If I push it for a longer time, he's going to end up faster than if I only push him for like, you know, half the distance. Okay, he's not going to get as fast. Okay, another way I could impart this energy is I could only apply 5 newtons of force, but let's do that again over the longer distance. Okay, so I've got 5 times 0.4. That's going to again give me 2 joules of energy. Okay, so you can see this work distance, this work force distance interplay here again, right? I can get the same amount of energy out either by applying a big force over a small distance or a small force over a big distance, and I can still get the same result from that. Okay? Either way, this graph number 1 is the one that's going to store the most energy because he had the bigger force and the bigger distance. So that's going to make this car get more energy and therefore be faster, right? So at the end, this is going to be the faster cart because he now has 4 joules of EK. These guys only have 2 joules of EK. So they're going to end up being slower, which should make sense if you think about it. Okay? All right, so that's what you're explaining again. Now, to get the equation, this one's a little bit trickier. So we're not going to go totally into it. So we know that the kinetic energy is the area. Okay, and again, I still have my force times distance. Okay, but in this case, we want to think of the force as more horizontal because it was this direction during the push I was applying that force. All right, if there's no friction, we know from Newton's second law, right, that the net F net equals ma, and in this case, this was the only force that I had. So that's this force here on the y-axis, all right? Because I know when I apply a force to a mass, it's going to accelerate or get faster, which is what we're talking about, all right? So instead of this force, we're now going to think of this as being mass times acceleration and then times the distance that you push it, okay? All right, so if you remember from last semester, we had this equation. We didn't really do the other one, but there's a couple of other equations that are like this that are called kinematics equations. Okay? Another one of these that you develop kind of in the same way looks like this. You don't need to know this. This is just so you wonder like where it came from. Okay? It's the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the distance. Okay? This is just another common physics equation that kind of comes from this, okay? And another equation. All right, that doesn't matter. All you need to know, right, is that this, do you see this AD here? There's an AD here also. So we're going to rearrange this equation and plug it in to be AD instead, okay? So if I do this, let's assume the initial velocity was 0 to keep it simple, okay? So then we're just going to call this V. So V squared equals 2AD, and if I divide by 2, then I just get AD equals V squared over 2. All right, so I'm going to put that here instead, and that makes this equation look like 1/2, which is the over 2 part, mass times velocity squared. Okay, you do not need to know this step. I do not care that you know that. If you're very, mathematically inclined and interested, you can figure out how that happens. Otherwise, I don't care. You just need to know that this comes from the area. Okay, because this force here is Newton's second law, ma. Okay, that's all you really need to know. Okay, all right, so if I'm thinking about how the variables interplay, right, if I want something to have more kinetic energy, right, if it's going faster, it's going to have more kinetic energy, or if it's more massive, it will have more kinetic energy. Okay, right, so here, do you see in this force thing, this is sort of secretly hiding the mass and the velocity in it because of the ma part, okay? Right? So you just need to know 2 things really, that mass and velocity can increase to change the EK, and that equation comes from the area, okay? If you're given it in graphical form, you should be able to know that the one that covers the biggest area has the most energy of whatever form it is, okay? If they cover the same area, they have the same energy. Okay? Good? All right, I think that wraps this one, I hope.